Hi, in this video, we will learn how to perform the Laplace transform using the property 7. We saw the relationship between the convolution and also the multiplication. The convolution represented by this symbol, and if you take the Laplace transform for ft convolution with the gt, in your Laplace domain you obtain fx multiplied with the gx. So convolution has a great application in engineering, where it shows the linear relationship for a system. Let's say you have a force which is equal to Ft, which is acting on a linear system. So linear system can be represented by Gt. If Ft and Gt are given, then how can you find the St? For a linear system, your Xt can be written in this formula, where it's equal to Ft convolute with Gt. So in the integration format, you can write it as 0 to t with respect to d tau, and your ft can be written into f tau multiplied with gt minus tau. In most of the case, your gt will be constant as long as the material property, mass, damping, stiffness, boundary condition remain constant. So if your ft change from one format, let's say you have sin t force acting on the system, so you can predict the response due to the sin force here by using this formula. Performing the convolution is out of scope in this study, so this is just for your extra information, where you can see the graphical representation for the convolution operation. So this is our convolution operation formula. So in simple, it can be written into this ft convolute with gt, and in detail it can be written in the integration format. So from this, to obtain the gt1 minus tau, so you can have initially your gt to be this function, and then g tau, you just change the t into tau. And when you take negative, it will be in opposite direction. So you take the t1 minus with tau, so that means it will shift to the right hand side. And then on the other hand, you have a forcing function ft, so which you change the t into the tau variable. Then when you multiply the first function and the second function here, you obtain the f tau multiplied with gt1 minus tau. So when you take this function multiplied with this, so you obtain this result. By finding the area within this curve, you obtain the answer for st1. So let's say let the t1 to be 2 in this case. So you can substitute all the t1 by 2, then you're able to find what is the magnitude for x when t is equal to 2 by using this formula. So if you want to find the position, what is the value for x when the t is equal to 3, so you just change the t into 3. And by solving this, you can get the answer for x3, and so on. So you can see that the convolution operation is complicated as it involves integration. So in this study, the main focus is you should know that we can simplify the convolution operation into a simple multiplication when you take the Laplace transform. So in this property, if you take the Laplace transform for two functions, which is in convolution, and in your Laplace domain, it will be just multiplication. Let's look at the proof for the property 7. So we have the fx multiplied with gx. From the Laplace transform definition, we can obtain this, where you have the function f tau and g sigma, where the tau and sigma are the dummy time variables. By using the Fubini theorem that you have learned in Engineering Mathematics 1, where if you have a double integral with respect to d sigma, you need to perform the integration inside first, and then only you integrate it with respect to the d tau. So if you perform d tau first, and then only perform with respect to d sigma, so you should get the same answer with this one. Both give you the same answer. And you have the tau and sigma variables, so you can separate it according to their own variables, like this case. Multiply between these two exponentials give you the negative x sigma plus tau. And this equation is in sigma tau plane or region where your tau is from 0 to infinity and your sigma is from 0 to infinity. Let's look at this term. You can see that when we let t equal to sigma plus tau, you can let the d sigma equal to your dt when the tau is equal to constant. So when this is constant, when you take the differentiation at both sides, you obtain dt equal to d sigma where your d tau equal to 0. Then we can change these two terms to t. So sigma here, based on this equation, you can obtain it to be t minus tau. And this remains. So the limit here, when your sigma is equal to 0, so substitute inside here, you obtain t plus tau, t equal to tau. So this is the answer. When your sigma is infinity, which is this one, you obtain the t is equal to infinity plus tau, which is equal to t equal to infinity. Substitute this information inside this equation, you obtain a new equation, and you found that all the variable is in t tau plane, where your tau is remain from 0 to infinity, and your t is changed from sigma to t, which is t is between tau to infinity. The region area for this equation can be written as this by excluding the function inside. So from here, t is equal to tau. When we plot it in the tau versus t, you obtain one linear line, and below it will be your region area for this. So if you want to find the region area with the t equal to 10 and tau is equal to 10 here, you can double integral with respect to dt and d tau. And you have to make sure the limit at the tau here, okay, your tau must be a constant. So the tau is from here, which is tau equal to 0 to here, tau equal to 10. So 0 to 10. Your dt is in this direction where you have, okay, you have this function here, t equal to tau, and then stop at here, which is t equal to 10. We also can find the region area by using this formula, where you can see we switch the order for the tau and also t. So in this case is dt d tau. The limit for the dt at the outside must be a constant. So your t here is starting from here, which is t equal to 0, to t equal to 10 here. Then you continue for the limit tau. So the limit tau must be a function. So your tau is moving upward. Okay, so your tau is from here. Okay, in this direction. You meet the tau equal to 0 here. So you substitute 0. And then you meet the tau at this line. So your tau is equal to t. These two formulas should give you the same answer for the region area at this component. You can see that this formula is similar to our previous problem, where instead of having 10, you have infinity there. So it's changed also from tau to infinity. So with that, we can convert it into this, which is 0 instead of 10, it will be to infinity, and for this part it will be just remain 0 to t. So this is d tau dt. So by performing the switch order, you can convert from this form to this form. Both of these formula find the same region area here for t equal to infinity and tau equal to infinity. Therefore, by switch the order of the integration, your integration limit with respect to dt, d tau can be changed to this limit. With that, you can see the order can be changed to this, and you have a new limit for that. Rearrange the term, we find that this is the convolution between ft and gt. And also, this is the function for the Laplace transform, and this equation is the Laplace definition. So therefore, this can be equal to Laplace transform for the ft convolute with gt. So you obtain the proof fx multiplied with the gx is equal to Laplace transform for ft convolute with gt. In this equation, we are going to find what is the yt. So to find the solution for yt, we can take the Laplace transform on both sides. So Laplace transform for yt gives you capital Yx. So if we look at this term, is the convolution between yt convolute with sine t. And when you take the Laplace transform for this term, the convolution will become multiplied in Laplace domain. Yt, after you take the Laplace transform, it becomes Yx multiplied with the Laplace transform for the sine t. So Laplace transform for sine t will be equal to 1 over x squared plus 1. So Yx remains. So this is the Laplace transform result for this. So you have negative in front, and yt becomes capital Yx. So this is the result for the left hand side. On your right hand side, Laplace transform for the t should give you 1 over x squared. Then you collect the term for Yx to get this answer, and then move this term to the right hand side. You should be able to obtain this. And x squared over x power 4 give you 1 over x squared, and then you have 1 over x power 4 here. So take the inverse Laplace transform to obtain the yt. So for the 1 over x squared, inverse Laplace transform to give you t. So for this term, okay, so you know that you have n factorial f n plus 1. So when you look at this, your n plus 1 is equal to 4. Therefore, your n is equal to 3. So substitute inside 3 factorial divided by x power 4. So when you take the inverse Laplace transform for this term, you should be able to obtain t power of n. So in this case, since your n is equal to 3, so you have t power of 3. So when you compare this term and this term, so you see the difference is on 3 factorial and the constant 1. So to obtain 1, you need to divide 3 factorial here. So with that, okay, so you have to divide 3 factorial, which gives you the result t power of 3 divided by 6. Therefore, we can conclude that when you assign the system with ft equal to t on this system, you obtain the solution yt to be this. These are the important properties for the convolution operation. For the first law, you have ft convolute with gt, which gives you this formula. And if you perform gt convolute with ft, you perform it in this formula. So if you perform these two formulas, both of them should give you the same answer. In the second law, when you take the ft and convolute with g1 plus g2, which is this formula, it will be the same when you convolute it separately, like this. And then for the third law, if you have f convolute with g first, and then later only you convolute with v, which is this formula, it will be the same as if you take the g convolute with v, and later you convolute again with the f. So both give you the same answer. So this is the most important property that we would like to discuss. When you take the impulse function, which is the delta, and convolute with g, and it will return you g. For example, in a mass spring system, if your forcing function is impulse, then you will get the response equal to impulse convolute with your system function, which is gt. And since we know if you take the impulse function, convolute with any function, it will return to be the function here. So therefore, you obtain the result to be gt, and you will find that your response is the same with the system function. For example, in the previous example, when your ft is equal to t, you get the response equal to this, but you don't know what is gt. So if you want to find out what is gt, then you can substitute this to be the delta function. Then, so once you let ft equal to delta function, and you get the response from it, and then this response will be equal to your gt, because your response is equal to your ft convolute with your gt, and since your ft is delta t, so any function convolute with delta t will return the gt function. Therefore, your response yt will be equal to gt here. So you need to be careful that convolution is not equal to the multiplication, where 0 multiply g, you should get 0. 1 multiply g, you should get g. But for convolution, 1 convolute g does not give g. 0 convolute g, it gives you 0. In this example, we are going to solve the ODE to obtain the yt. This ODE can represent a mass spring system, and on the right hand side of the ODE is the external force acting on the system. So in this case, your force is delta t, which is the impulse function. So at t equal to 0, the impulse function has the magnitude equal to 1. The initial condition is given where the y0 and y prime 0 is 0. Let's take Laplace transform on both sides. So on your right hand side, Laplace transform for the delta t gives you exponential negative ax. So in this case, t minus a, your a is equal to 0. With that, substitute inside it, you obtain exponential 0, which gives you 1. So on your right hand side, you obtain 1 here. So Laplace transform for y double prime gives you x squared minus x minus 1. Then you have a capital Yx, initial condition y0, and y prime 0. So since y0 and y prime 0 is 0, so you only have x squared yx, which is this term. So Laplace transform for 3y prime t, y prime t gives you capital Yx, and then since it's the first order, you have x minus with 1, which is the y0. Don't forget your 3. So this is the result for Laplace transform 3y prime t. So since your y0 is 0, so we can cancel it, then you obtain 3x yx, which is the second term here. And lastly, Laplace transform for 2yt. give you 2yx. And you collect the term for the yx, move this term to the right hand side, then you get this. Check the root for this polynomial, then you will find x is equal to -1 and -2. So with that you can form s plus 1 and s plus 2. When you multiply together, you will get x squared plus 3x plus 2. So therefore, you can obtain this term here, and you can see there are two linear factors, x plus 1 and x plus 2. So you can use the partial fraction to obtain this. Then we have to take the inverse Laplace transform to obtain the yt. So inverse Laplace transform for 1 over x plus 1. So in general, x plus a, if you take inverse Laplace transform, then you should be able to obtain exponential negative at. Since your a is equal to 1, then you obtain exponential negative t for the first part, then negative with 1 over x plus 2, where your a is equal to 2 here, so you need to minus exponential negative 2t. So this is your answer for your yt. Therefore, we can draw this where you can see your force is equal to delta t, and your system, let it to be gt. So ft convolute with your gt, it should give you the output response, which is equal to yt, where you success to find the yt by using the Laplace transformation. And this is the graph for the yt. How if you want to find the gt? How can we get it? So in this case, we can use the identity. From the identity property of the impulse function, when you take the delta function, convolute with g, then you will get back the g. So in this case, for a linear system, if you take delta convolute with the system function, which is the g, then you get the response function, which is yt. So when you compare this and the second equation here, you will find that your yt will be equal to your gt. So therefore, your gt will be equal to this answer. In this case, if the gt is known and is given, so based on the ft function given, you can convolute it to obtain your response yt. But this process is very time consuming because we have the integration. So instead of performing the convolution operation, we can perform the Laplace transform on the time domain function and convert it into the Laplace domain function. So by doing this, we can change the convolution into multiplication. So our response will be just equal to fx multiplied with gx give you the yx. So once you obtain the result for the yx, you can obtain the yt by using the inverse Laplace transform. So multiplication in Laplace domain is very fast and easy compared to the previous method.